Today, we will be observing the motion of a falling object. Let's look at the objectives of the lab. We're going to be using a software called Tracker to analyze the position and time of the object. Afterwards, we're going to be using another software called vIDLE to construct a computational model based on the principles of Newton's second law that includes both the gravitational and drag forces. Finally, we're going to be comparing the predicted and observed models. Let's go look at some concepts first. The momentum principle says that the force is equal to the change in momentum over the change in time. According to Newton's first law, an object moves in a straight line and at a constant speed except when it interacts with other objects. So we're going to be making some assumptions that includes that net force is equal to the weight force, where weight force is equal to the mass of the object, which is 0.24 kilograms in our case, times g, which is 9.8 meters per second squared, times j hat, where j hat is a vector 0, 1, 0, because the object is falling in the y direction. If we include drag force is equal to negative b, which is the drag coefficient, times the object's velocity. So our assumptions in this case is that 1, the net force is equal to the weight plus the drag force, and 2, that there's a positive correlation between speed and drag force. So more speed is equal to more drag. So in my experiment, I dropped an orange at a specific height. So as you can see from Tracker, I dropped this orange at a specific height. And then afterwards, I found the model, and as you can see, it's a pretty parabolic curve. Afterwards, I used vIDLE, and I included drag force in my equation. So as you can see, it's the mass of the ball times g times j hat. And drag force is equal to the ball's velocity times the magnitude of the ball's velocity times the coefficient negative b, which I found using experimental calculations. So if I run it for you, here's the simulation. Afterwards, I graphed both of them on Excel, and then I compared the two graphs. So where the dark blue line is the predicted model using vIDLE, and the light blue line is the observed model using Tracker. And as you can see, there is some variation near the bottom here. I can probably find a better representation of drag force by adding in the cross-sectional area of the object. This will probably give me a better estimation. As to why the curve is not completely perfect, it's most likely due to video distortion. So if we go on to the first question, what does it mean? So which model predicts the terminal velocity? Terminal velocity is the maximum velocity an object can have due to air resistance. So with terminal velocity, the object will later on have constant velocity because the air resistance or drag force will exactly balance the weight force. So as you can see, I plotted my velocity versus time model, and it should flatten out here because the acceleration should go to 0. So as terminal velocities approach, as the velocity slope flattens, which is over here, the reason why it's not completely flat is probably because my observation time is too short. So if we go on to our second question, what if I threw the object rather than just dropping it? My prediction was that it would converge, and after I graphed it, you can see that the velocities converge because later on at some point the drag force will balance the weight force. So here is the velocity if I just drop it from a specific height, and here is the graph if I just throw it down at a specific height. And as you can see, the velocity converges to the exact same answer afterwards. So my result is that there's a variation in the predicted and observed models due to drag force exerting an upward force on the object. Thank you very much.